So we are going to see today the third theorem. Your language L is accepted by some epsilon NFA if and only if L is accepted by some DFA. That is, there exists a DFA, then there exists a equivalent epsilon NFA. There exists a epsilon NFA, then there exists a equivalent DFA. This is what is the proof. What we have to prove. That is the equivalence between DFA and epsilon NFA. So we are splitting the theorem into two parts. We are taking first the if part and then the only if part. So we are first proving the if part and then we are going for a only if part. So what is your if part? If part is, what is our if part? If part is, we want to assume that there exists a DFA D, then there exists a equivalent epsilon NFA. So given DFA, we want to find or we want to say that there exists a equivalent epsilon NFA for this DFA D. This is what is the if part proof. So we want to, that is what we want to construct epsilon NFA E from the given DFA by adding the following transitions. So how can all the other things are the same, the state and the input symbol and the start state and then the final state, all are similar to your DFA. Only thing that gets differ from DFA is the transition. So how the transitions are going to differ, that is what we are going to see in the next slide. So for each state Q in DFA, for each state Q in DFA, in the epsilon, that is, in the NFA, epsilon NFA, we want to add a epsilon transition stating to null. And another thing is, we want to convert each transition of DFA on the input symbols given in the DFA to equivalent NFA transitions like del n of q comma a is equal to del p. So here in DFA you are having on state q giving input a, it goes to the state p. Then here also in NFA you want to say that on state q with input A it goes to the state P. The difference is here it is simply P, here we are saying it as a set P. So that is what the way you want to prove our if part. So for each state Q in DFA you are having an equivalent transition pointing to a null transition. And for each transition in a DFA, you are going to have a transition in NFA going to the set containing only P. So thus the transitions of epsilon NFA and DFA are the same. And the difference is only on the extra epsilon transition from every state to itself. The language accepted by the given DFA and the constructed epsilon NFA is the same. So we'll go with an example. So this is the given DFA. This is a given DFA and we want to find the equivalent epsilon NFA E. So the language is the same. The DFA accepts B star A star or B star and the epsilon NFA is also the same and the language accepted is also the same. The difference lies only in the transition. So this is what, so you are adding, so there are two states in DFA, Q0 and QF. So for these two states you are going with the transitions Q0 comma epsilon is equal to null and QF comma epsilon is equal to null. And then for each transition in DFA you want to add transition in NFA also. So that is what is the thing given here. So for each transition in DFA on state Q0 with input symbol A, it goes to QF. So in your NFA, you are having on input Q0 with input symbol A, you are going with QF, set QF. That makes the difference. So for each transition, you are introducing a transition in NFA also. So this makes the difference. Thus, you constructed a equivalent epsilon NFA for a given DFA. Both the languages are the same. Since the transitions are the same, definitely the language accepted by both the DFA as well as the epsilon NFA is going to be the same. Thus, we have proved the if part. So now we are going to see the one leaf part proof. So what is your one leaf part? Here we have to assume that there exists a epsilon NFA for which you want to construct a equivalent DFA that accepts the same language as that of a epsilon NFA. So we want to construct the DFA from the epsilon NFA by means of the modified subset construction method. So you have given with the epsilon NFA, which is having a 5 tuples, that is the set of state QE, input symbol, del E, start state Q0, and set of final states FE. Then you want to find a equivalent DFA, the same 5 tuple, but how we are going to get QD from QE. The input symbol is the same for both epsilon NFA and epsilon DFA, so we are kept it as sigma in both the cases. And you want to find the transition for DFA from the transitions of epsilon NFA, and start state of the DFA from the start state of the epsilon NFA, final state of the DFA from the final state of the epsilon NFA. So how we are going to do this? With respect to the start state, as per the modified subset construction method, the start state of DFA can be obtained from the start state of, so here the set of states, not it is the start state, it is actually the, it is not the start state, it is actually the state of DFA. So how we are going to get the state of DFA? The states of DFA or the epsilon closed subset of the states of your epsilon NFA. That is, we can say that as QD is equal to 2 power QE. So all this 2 actually the number of states in QD is going to be, actually the number of states in QE is QD is going to be much lesser than 2 power QE. Most of the states will not be, most of the states in 2 power QE will not be the states of the QD, but some of the states will be there. But the difference is here you want to take the epsilon closure of the state. So this is how we are obtaining the states of DFA from the states of your epsilon NFA. And with respect to the input symbol, this is the same as that of the epsilon NFA. And with respect to the start state of DFA, you want to obtain the start state of DFA from the start state of NFA. But here what you have to do is you have to take the epsilon closure of the start state of epsilon NFA to obtain the start state of the DFA. So definitely this is going to be the set. Definitely this is going to be the set we are going to obtain as a start state of the DFA, taking the epsilon closure of start state of epsilon NFA. And that is what the thing given here as epsilon closure of Q0. And what about the final state of DFA? With respect to the final state of DFA, the set containing at least one final state of epsilon NFA is going to be the final state of your DFA. That is, let us assume you are having yes a set in a subset in epsilon NFA, and that subset is a valid state in DFA. Then that will be a final state only if it is having a final state of your epsilon NFA. Otherwise, it is not a final state. So simply, if the state in a DFA contains any one of the final state of epsilon NFA, then that is also a final state of your DFA. So what about the transitions of DFA? So the transitions of DFA has to be computed from the transitions of NFA. So for all input symbol that is present in the sigma and for all the states that belongs to the state in DFA, we are going to construct the transition as follows. So let us assume the set S is equal to, you are having a set which is nothing but a state in DFA, and the state consists of the states P1, P2, Pk of your NFA. These are all the states that are present in epsilon NFA. Then you want to compute the transitions over the symbol, that is A symbol, in your, that is your epsilon NFA transition, the transitions that is present in epsilon NFA from each state. So let us assume you are in P1, in state P1 with input symbol A in epsilon NFA. If it goes to R1, then take that R1. With the state P2 with input symbol A in epsilon NFA, it goes to R2, then take R2. Likewise, you are going with R1, R2, etc. up to Rm. So this is what the set of states you are obtaining in epsilon NFA on input symbol A from this set of states P1, P2, etc. up to Pk. Then the equivalent DFA transition is obtained by taking the epsilon closure of these sets R1, R2, Rn. So how we are going to obtain this epsilon closure? The thing is very simple. You want to take epsilon closure of R1 union epsilon closure of R2 union epsilon closure of R3, etc. up to union epsilon closure of Rm. You are going to get a set, and that is the state which goes from this set, this state P1, P2, etc. That is this state S with input symbol A. It goes to that particular set. So that is what, how we are obtaining the transitions for DFA. So what then we want to prove now? The thing what we want to prove is, we want to say that the language accepted by the DFA what we have constructed and the language accepted by the given epsilon NFA are the same. So this has to be done based on the induction method, and here the induction proof, based on the induction proof, and the proof is on the length of the word W. So what we actually have to prove is, we want to say that the sequence of on applying the epsilon NFA transitions sequentially from Q0 and processing each word in W, each letter in W, we are going to obtain some state, and that will be equal to the same starting from the start state of DFA and processing each character of the word W on applying the transitions of the DFA what we have obtained. We have to reach the same set of states as by this epsilon NFA. If both are same, then we are proving that the transitions are generating the same languages as like epsilon NFA, the DFA also. So that is what we want to do. So here we want to take the basis. With respect to basis, we are taking the length of the string as 0. So we are taking the word as epsilon. So what we want to say on applying, that is starting from the start state Q0 and epsilon NFA on the input symbol epsilon, what are all the states we are going to obtain? That is nothing but the epsilon closure of Q0 as per the definition of epsilon closure. So that is what you are going to obtain. And what about the case of DFA? Since we have taken W as epsilon, we can say that del cap of, that is del. So here this is what is the thing. So NFA transitions on epsilon from Q0 gives you a epsilon closure of Q0 as per definition of epsilon closure, which is nothing but your start state of QD based on the start state of DFA. We have obtained the start state of DFA by taking the epsilon closure of the start state of epsilon NFA. So it is equal to QD, which can be written as del transitions, that is DFA del transition from QD comma epsilon. This is by means of the definition given in the DFA. So since in DFA on epsilon input, it goes to the same state. So it definitely goes to the same state QD on epsilon. So whatever state epsilon transition goes to the same state, since your DFA does not have a epsilon transition from one state to another state. Thus we have proved the basis. The NFA, that is from the starting state Q naught on input symbol epsilon, and in epsilon NFA, and the same way in epsilon and the same way in DFA, both are going to the same thing. Thus we have proved this. Now we want to go for the assumptions, that is we want to take the induction hypothesis. What is the hypothesis? Is we want to assume given statement is true for the W whose length is K and whose value is X. We are assuming that the statement is true, and also we are assuming that the epsilon NFA starting from Q naught and processing all the character of the string X, and the transition in DFA starting from the start state of DFA QD and processing each character in the string X, both obtains a set of state P1, P2, etc. up to Pk. So this is also we are assuming to be true. Keeping this statement and the basis, we want to prove for the length of the string K plus 1 the statement is true. So the induction is, we are taking W as XA. So one character is added to the, one character is concatenated to X. So the length becomes K plus 1. And then we want to prove that the transition, epsilon transition, sorry, not epsilon transition. The epsilon NFA transition starting from Q naught, processing the string XA, reaches to some set of state, and in another word reaches to the final state of epsilon NFA. Then the constructed DFA starting from the start state QD of DFA, processing the string XA, also reaches to the final state of the constructed DFA. If this is done, then we are proving the induction part. So now we are taking our epsilon NFA transition. So we are taking from Q naught, the start state of epsilon NFA, and then the string XA. As per the inductive hypothesis, we know that, this is where the inductive hypothesis, we know that Q naught comma X, that is in epsilon NFA starting from Q naught, processing the string X, we are getting a set of state P1 X, comma P2 etc. up to Pk. This one is true with respect to our hypothesis, with respect to our assumption. And as per the definition of our extended transition in epsilon NFA, we can write this as, so how will we find the states from this transition? So this transition can be obtained, the states from this transition can be obtained by taking the union P1 comma A del E of P1 comma A union del E of P2 comma A union del E of P3 comma A etc. up to del E of Pk comma A. That is what written here like this. So I is equal to 1 to K. We have to find the state where your epsilon NFA is going from the state Pi on taking the input A. So as per the definition of extended transition of epsilon NFA, it is going to have a set R1, R2, etc. Rm, and we want to take the epsilon closure. That will be the set which actually the NFA goes, epsilon NFA goes from this set of state P1, P2, Pk on input E. So that is what the thing given here. Epsilon closure of R1, R2, etc. Rm as per the definition of extended transition of NFA. Now we want, this is the left hand part of the first equation what we want to prove. This is the left hand part of the equation what we have to prove, and we have told that it goes to this value and we name that as 2. And now we are going to take the right hand part. So the right hand part, we want to find the transition sequences in a constructed DFA from the given epsilon NFA. So what, as per the hypothesis again, we can say that we have to start from the start state DFA, and on the input string X, it goes to the set of states P1, P2, etc. up to Pk. This one is true as per our hypothesis. And as per the subset construction method, we know that if you are having this set P1, P2, etc. up to Pk, this is one single set in DFA. And how we are going to obtain the resultant set is, we want to find what is P1, A, what is P2, A, and where the state goes. If we take the epsilon closure of that state in NFA, in your epsilon NFA, that is what, taking the epsilon closure of the transition of P1, A, P2, A, etc. up to P, A in epsilon NFA gives you the state for a del cap of D. So this we are taking as a equation 3. So already we have told that, from the equation 2, that is from the left hand part is also obtaining this one, and the right hand part is also obtaining this one. So from 2 and 3 we have proved that the equation del cap E of Q0, Xa is equal to del cap D Qd, Xa. Thus we have proved the one leaf part. So considering both if part and one leaf part, we proved the equivalence between epsilon NFA and DFA. That's the proof for the theorem.